Hello. Today we're gonna learn about reinforcement learning. What it is, how it works, and how it can enhance your business. Bam! Hello! You guys. Too nice. So, without further ado, we're going to talk about reinforcement learning, what it is, how it works, and how it can enhance your business. I'm going to be honest, I am not a very good businessman. And so I'm going to give you some ideas, but that's all. Anyways, in between now and then, we're going to talk a lot about reinforcement learning. So imagine it was snack time, so maybe 2 or 3 hours from now, and you had to choose between going to Squatch's Fry Shack or Norm's Fry Hut for a delicious French fry snack. Who likes fries? I like fries. Okay, good. So we all understand this example. This is an important thing to figure out. Okay, so there are a lot of ways we could pick out one of the two places for a snack. For example, we could just flip a coin. If we got heads, we could go to Squatch's. And if we got tails, we could go to Norm's. However, just flipping a coin wouldn't take into account how hungry you were. I just ate lunch, so I'm not starving. And some other days, we might be more hungry than others. Also, flipping a coin doesn't take into account how many fries we get at each place, which is important. For example, we might usually get a lot of fries at Norm's, and that would be great if we were really hungry. But maybe less great if we were not so hungry. Like if someone handed me a huge pile of fries right now, I'd be like, ugh. So it is possible, it's also possible that Norm might give us a skimpy order of fries, and maybe 1 or 2 fries right now would hit the spot. But if we're really hungry, that would be a total bummer. Okay, in contrast, if we were not very hungry, it might not be so bad. Likewise, a Squatch might serve as a skimpy order of fries or a large one. And depending on how hungry we were, each order could be good or bad. So it would be nice if we had a way to decide which place to go to for a snack that took hunger into account, as well as the possibility that we could get a large or skimpy order of fries at each place. So to solve this problem, of course, this is the obvious way to do it, we're going to use a neural network that takes our hunger as input and gives us the probability that we go to norms, P norm, as the output. The only problem is that we need to train this one bias. So this is a great neural network. I went ahead and trained the weight, but for some reason I left out the bias just so we could have a little example to talk about. And now usually when we train a neural network, we would start with a training data set like this. That has possible input values, like how hungry I am on a scale of 0 to 1, paired with their ideal output values. So if I'm super hungry, I want to go to Norm's. And if I'm not hungry, I want to go to Squatch's, apparently. With this type of training data, we could train our neural network with standard backpropagation. If you're not already familiar with backpropagation, don't worry, we'll review it in just a bit. However, in this example, that's just the way Norms talks. However, in this example, we don't know in advance if Norm or Squatch will serve us a large or small order of fries. And that means we don't know in advance what the output value should be. Josh, if we don't know what the output value should be, how can we train our neural network? When we don't have a known output values in our training data set, we can still train our model using reinforcement learning. There are lots of different reinforcement learning algorithms for training neural networks, but in this video or this talk, we're just going to focus on one called policy gradients, and it's going to be real simple. This is one of the easiest ones, and so you know what Squatch says? Bam. Okay, now before we dive into reinforcement learning and policy gradients, I want to do a quick review of traditional backpropagation to see how it works so we can understand its limitations and see how policy gradients overcome them. So for now, let's just assume that we have this training data and we know the desired outputs in advance. Given this data, we could run the input values through the neural network one at a time and quantify the differences between the output from the neural network and the ideal values. Boop, boop, boop. Then, if we wanted to, we could calculate the differences for different values for the bias. Boop. And draw a graph that shows how the differences change with different bias values. Then, using a randomly selected bias value, we could calculate the derivative of the differences with respect to the bias. So that green line is our derivative. And because the derivative, the slope of this green line is negative, we would know that the value for the bias that minimizes the difference and thus results in a better fitting model is to the right of the current value. In other words, when the derivative, the slope of this green line is negative, then we need to shift the value for the bias to the right on the x-axis. Alternatively, if we used this value for the bias to calculate the derivative, then the derivative, the slope of this green line, would be positive, telling us that the optimal value is to the left of the current value for the bias. In other words, when the derivative, the slope of this green line, is positive, then we need to shift the value for the bias to the left on the x-axis. In summary, when the derivative is negative, then we need to shift the value for the bias to the right, and when the derivative is positive, we need to shift the value for the bias to the left. Lastly, the derivatives can correctly tell us which direction to shift the bias because the training data contains the ideal output values. So this is how backpropagation normally works. Bam. However, the problem is we don't know in advance where we can consistently get a small or large order of fries. And that means our data set can't have the ideal output values. And without the ideal output values, we can't calculate the differences between them and the outputs from the neural network. And without those differences, we can't calculate these derivatives. And without the derivatives, we don't know if we should shift the value for the bias to the right or the left. Josh, what are we going to do? Well, it turns out we don't actually need to know the ideal output values in advance to calculate the derivatives. Instead, we can guess what the ideal output values should be and use those guesses to calculate the derivatives. Bam! Yes! Now let's walk through our example and see how reinforcement learning and policy gradients can use guessing to make this work. We'll start by assuming we're not hungry. And that means we'll plug, because we just had lunch, right? And that means we'll plug 0.0 into the neural network. Now we just do the math. Beep, beep, boop, boop. You can sing along with me if you want. Beep, beep, boop, boop. Beep, 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 boop, 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 beep, 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 boop. And the probability that we'll go to norms, p norm, is 0.5. And that means the corresponding probability that we'll go to squatches, p squatch, is 1 minus p norm, which is also 0.5. In other words, we can draw a line that is 0.5 units long to represent the probability of going to squatches, and then append another line that is 0.5 units long to represent the probability of going to norms. And we end up with a line that goes from 0 to 1. Now, to decide which place we'll visit for a snack, we pick a random number between 0 and 1. In this example, we randomly pick the number 0.2. And because 0.2 is in the region that represents Squatch's Fry Shack, we'll go there. Now comes the part where we make a guess. if we make a guess that the correct thing to do is to go to Squatches when our hunger is 0.0, oop, I got excited. Then, ideally, we would want the probability of going to Squatches, P Squatch, to be 1, right? If we're supposed to go to Squatches, we want the probability to be very high. And that means, ideally, we want the probability of going to norms, P norm, to be 0 or very low. Now, given these ideal values that are based on a guess, we can quantify the difference between the ideal value for P Squatch, 1.0, and the actual value for P Squatch, 0.5, that's based on the output from the neural network. And that means we can calculate the derivative of the difference with respect to the bias that we want to optimize. Bam. Josh, how exactly do we calculate this derivative? That's a great question, Squatch, but it's out of the scope of this talk. For now, the most important thing to know is that the guess makes it possible. Anyway, given that our guess to going to Squatch's place is the best thing to do, the derivative ends up being 0.5. And if that guess is correct, then the positive value for the derivative tells us to shift the value for the bias to the left. On the other hand, if our guess is incorrect, then we should have gone to norms instead. Then we'll want to do the exact opposite of what the derivative tells us to do. In other words, instead of shifting the value for the bias to the left, we'll want to shift the value for the bias to the right. But Josh, how will we know if the guess is correct or not? In other words, how do we know if we should shift the bias to the left or the right? The answer is simple, Squatch. We just order some fries. Bam! In this example, when we order some fries, we get this relatively small serving. Hey, Squatch, how come our order of fries is so small? I couldn't resist and I ate some of your fries. Well, this time, I guess that's okay. It's okay because our hunger level is 0.0, meaning we're not hungry at all. So it was actually a good thing that Squatch ate some of our fries. In other words, getting a small order of fries when we're not hungry means we made the correct guess. Bam. And since we made the correct guess, we set something called a reward to a positive value. To keep things simple, we'll just pick 1.0. In contrast, if Squatch had given us a large order of fries, then we wouldn't be hungry enough to eat all of the fries. And that means we made the wrong guess, because there's nothing worse than a wasted fry. So in this case, we would set the reward to a negative value. To keep things simple, we'll just use -1. Okay, I get that a positive or negative reward reflects if our guess is correct or not. But how does that help us interpret the derivative that we calculated earlier? We simply multiply the derivative by the reward to get an updated derivative that points us in the correct direction. Bam! In this example, we were not hungry, and Squatch gave us a small order of fries, so we made the correct guess, and the reward equals 1.0. And multiplying the derivative, 0.5, by the reward, 1.0, means the updated derivative is the same as the original derivative. Beep, boop. And the positive, updated derivative tells us to shift the bias to the left, just like the original derivative. In other words, when we make the correct guess to begin with, then the derivative that is based on that guess points us in the correct direction. In contrast, if we were not hungry, but Squatch gave us a large order of fries, then we would have made the wrong guess. And the derivative would be telling us to do the opposite of what we should do. However, multiplying the derivative by a negative reward for making the wrong guess would flip things around. And then the updated derivative would correctly tell us to shift the bias to the right. In other words, if we made the wrong guess to begin with, then multiplying the derivative, which is based on that guess, by a negative number will flip things around and point it in the correct direction. This is super important, so let me repeat it. When we multiply a derivative that is based on an incorrect guess by a negative reward, we flip the direction and correct the mistake. Bam! In summary, when we multiply the derivative by the reward, we end up with an updated derivative that tells us how to modify the bias correctly. Bam! A lot of bams. I hope that's okay. Now, when we multiply the derivative by 0.5 by the reward, we get the updated derivative, 0.5. And then we plug the updated derivative into gradient descent or the optimizing algorithm of your choice and do the math. These details are not important. All you need to know is we get an updated value for the bias, which in this case is negative 0.5. Now we plug the new bias term into our neural network. Beep, boop. Bam. Now that we have the updated bias, we have to get some more fries so that we can keep optimizing it. So we plug in our hunger level 0.0 because we just ate fries. And when we do the math, the probability that we will go to norms is now 0.4. And that means the probability we go to squatches, 1 minus p norm, has increased to 0.6. And the probability that we go to norms has decreased to 0.4. And remember, the last time our hunger was 0.0, we went to squatches. And we got what we wanted. We were full, we weren't hungry at all, and Squatch ate all our fries, and that was actually a good thing. So it makes sense that, given the same hunger as before, we now have a higher probability of going to squatches. Now we pick a random number between 0 and 1, and we get 0.9. And because 0.9 is in the region that represents Norm's fry hut, that's where we'll go. Now, in order to update this bias, we have to calculate the derivative. And in order to calculate the derivative, we have to make a guess that going to norms was the right thing to do. And if going to norms is the right thing to do, then ideally the probability of visiting norms should be 1.0. Making the guess allows us to quantify the difference between the output from the neural network, 0.4, and the ideal value, 1.0. And with that difference, we can calculate the derivative with respect to the bias. This time, when we calculate the derivative, we get negative 0.6. Now we need to determine if we made the correct guess, so we know if we should shift the bias to the left or the right. So we order some fries. And Norm gives us a huge pile of them. Normally, this would be awesome. Unfortunately, we aren't hungry. Remember? The input to the neural network is 0.0. And since we're not hungry, the fact that Norm gave us a huge pile of fries means we made the wrong guess. So the reward equals negative 1. Now we multiply the derivative by the reward to get the updated derivative. Beep, boop, boop. Note, the updated derivative, 0.6, is positive. So that means we need to decrease the value of the bias a little bit more. We then plug the updated derivative into gradient descent and do the math. Beep, beep, boop. Now we plug the new bias term into the neural network. Beep, boop, bam. Now if we plug 0.0, which means we're not hungry, into the neural network, the probability that we will go to norms is even smaller than it was before. Now it's 0.2. And again, that makes sense that the probability that going to norms is getting smaller. Because so far, each time we've plugged a 0.0 into the input, we should have gone to squatches instead of norms. And that means that the reinforcement learning algorithm we're using, ordinary policy gradients, is working. Double bam. Now that we understand the main idea of how reinforcement learning works, let's talk about how we could use it in a business context. This is a super simple example. Let's imagine we owned a toy store that only sold 2 toys, a rattle and a robot. Now, if someone was shopping at our website for a rattle, then since we only sell one other toy, a robot, it makes sense to promote it on the same page. So when you just have 2 products, we don't have to worry too much about what products to pair together. But things get a little more complicated and more interesting when you have 3 or more products. Now it's not so clear what toy to pair with the rattle. And this is where reinforcement learning can really come in handy. In this case, using reinforcement learning to train a simple neural network or even a simple logistic regression would probably work just fine. So here we have a neural network that uses shopper ID and previous purchases to determine which products are paired. Bam! Now let's talk about how reinforcement learning with human feedback works with large language models, because that's kind of why we're here. How are we doing on time? I think I'm doing really well. Okay, imagine we wanted to build and train the next ChatGPT or DeepSeek from scratch so that we could ask it a really important question. What is StatQuest? And it would generate a polite and helpful response. StatQuest is an awesome YouTube channel for learning about AI. That means we need to learn how to train this untrained decoder-only transformer model. By untrained, we mean that all of the weights and biases in the model are just random initialization values. For example, if we gave this untrained model the prompt, "What is StatQuest?" then, because the model is untrained, all it will generate is blah, 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 blah. And since blah, 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 blah is not a particularly polite response, and it certainly isn't helpful, we need to train this model. The first step in training a large language model is to train it to predict the next token in a really large body of text, like the entire Wikipedia. For example, we could start with the article about "ah" and use the tokens for the phrase "ah" was a Japanese to train the model to predict the next token, girl, using normal backpropagation. And then we might use "was a Japanese girl" to train the model to predict the next token, group. Likewise, we would just keep using fragments from Wikipedia articles to train the model until we got to the very end, where we would use "of horizontal points has been" to train the model to predict the next token, changed. Terminology alert. Even though we're training the model to predict the next token in terms of large language models, this is actually called pre-training, which personally I find a confusing terminology, but whatever. Thus, by pre-training our untrained model to predict the next word with a huge body of text, we end up with a pre-trained model. Pre-training an LLM results in a model that is pretty good at taking bits of Wikipedia articles and predicting the next token. However, this is not how anyone actually uses ChatGPT or DeepSeek or whatever. For example, a Squatch has never prompted an LLM with "of horizontal points has been." and expected to get the response changed. Instead, we usually enter prompts like these. What is a good YouTube channel for learning about AI? And expect a polite and helpful response like, StatQuest is a good channel to learn of AI, bam. In other words, when we prompt an LLM with a question, we expect a response that is both polite and helpful. So our model, which so far has only been pre-trained to predict the next token, is said to be unaligned from how we actually want to use it. So that means we need to align the pre-trained model to the way we actually expect to use it. Aligning a pre-trained model usually takes 2 steps. 1, supervised fine-tuning, and 2, reinforcement learning with human feedback. Supervised fine-tuning uses a dataset with pairs of human-created prompts and human-created responses. For example, someone might write out a prompt like this. What is a good YouTube channel for learning about AI? And that same person, or possibly somebody else, might write out a response to that prompt like this. StatQuest is a good channel to learn about AI, bam. And given a prompt paired with a response, we could use normal, everyday backpropagation to train the model to generate this response. As a result, supervised fine-tuning turns our unaligned pre-trained model into a model that has started to be aligned and can generate polite and helpful responses to specific natural language prompts. Bam. Note, because creating these prompts and responses is done by real people that need to be paid for their work and takes a long time, the dataset for supervised fine-tuning is relatively small compared to the dataset for pre-training. As a result, supervised fine-tuning can easily train a model to overfit the data. In other words, our model might respond appropriately to this specific prompt, but it probably does not generalize well to new prompts that were not part of the supervised fine-tuning dataset to begin with. So, after pre-training followed by supervised fine-tuning, we have a model that is somewhat aligned to the way we plan to use it. It can respond appropriately to prompts it was specifically trained on, but not to new prompts. Hey Josh, how do we train the model to respond to new prompts? Well, the ideal way to deal with overfitting is just to use a super huge fine-tuning dataset. Unfortunately, creating a super huge fine-tuning dataset would cost a super huge amount of money. So instead of spending a super huge amount of money on building a super huge fine-tuning dataset, we can use reinforcement learning with human feedback to train our model to generate appropriate responses to prompts it wasn't initially trained on. Bam! The first step in understanding reinforcement learning with human feedback is to understand that given a specific prompt like this, what is a good channel for learning about AI, we can configure a model to always select the output with the highest value for each token and thus generate a specific answer every single time, like this. StatQuest is a good channel to learn AI, bam. Alternatively, we could use the outputs from the softmax function as the probabilities that each token is selected. And when we use the probabilities to select the output token, the token with the highest value will be selected more frequently than the others, but other tokens still have a chance at being selected. And as a result, we can get different outputs like this. StatQuest is a great channel for learning AI, double bam. Or this. StatQuest is an awesome channel for learning about AI, triple bam. That's my favorite. So given these 3 generated responses to the original prompt, we can list all possible pairs of responses. And for each pair of responses, ask people to tell us which one they prefer. Asking people to list their preferences is much faster than asking people to write out the response that they think is that they think is best. And these preferences are the human feedback bit in reinforcement learning with human feedback. Bam. Now that we have the preference data, we can use it to train a model to give relatively high scores to the preferred options. Hey Josh, I'm not sure I understand what you just said. Can you give me an example? Yes. To train a model to give relatively high score to preferred options, we first make a copy of our model that has been through supervised fine-tuning. We then modify the model by removing the unembedding layer. So the output layer, instead of outputting tokens and generating text, we get rid of that. And we replace it with a single output. And the result is a new model that we will train to calculate rewards for reinforcement learning. Remember rewards from the first part of this talk? Positive and negative rewards. Now, given the human feedback preference data we collected earlier, we can train this model to generate a positive value or positive reward for the preferred response to the prompt. And we can train the model to generate a negative value or negative reward for the response to the prompt that was not preferred. Wah, wah. Once we're done training this new model, which is called the reward model, we can use it to train the original model that only had supervised fine-tuning. To train the original model with the reward model, we start with new prompts that were not part of the supervised fine-tuning dataset, and we don't have human-provided responses for, like this. What's another good YouTube channel for learning about AI? And we have the original model generate a response, like this. YouTube is special. Now, that's not a useful response. And so when we run that prompt and the generated response through the reward model to calculate a reward, because the response is not helpful, it will get a negative reward from the reward model. And then we can use the reward to train the original model. Then, after training a bunch with reinforcement learning, our prompt, what's another good YouTube channel for learning about AI, results in a polite and helpful response. Serrano Academy is a great YouTube channel for AI. That's what I'm talking about. Bam! And because this response is both helpful and polite, we have, excuse me, I got all excited. Did I skip a slide? What happened? Oh, I did. I went backwards. What's going on? Something's wrong. Okay, anyways, once we finished, because this is, hold on. What? Blah, 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 blah. I've been up here for too long. Okay, because this is helpful and polite, we're done. We're done training. That's all I wanted to say. It's that easy. Why did I have to delete the slide that said that? I don't know. Okay, once we finish training the original model with reinforcement learning with human feedback using our reward model, we end up with a final model that is both trained and aligned to the way people actually want to use it. What is StatQuest? StatQuest is, with Josh Starmer, is an awesome YouTube channel for learning about statistics, machine learning, and AI triple. Yes! Sorry for the shameless self-promotion, by the way. I've just been doing it this entire seminar. But are we done? No. Usually I finish on a triple bam and we're done. But today we have a little bonus. Okay, check it out. Hey Josh, I've got a question. How do we use this in a business setting? In marketing and sales, we can combine reinforcement learning with human feedback with A/B testing. A/B testing, are you guys familiar with A/B testing? Mostly. A/B testing is like, well, I'll just go through an example and you'll figure it out. It's not that hard. It's comparing two things and finding out which is better. Okay, for example, we can create two different thumbnails for a YouTube video. And one will get more clicks than the other. And that is your human feedback. That's free. You know, we don't have to hire a bunch of people to give us human feedback. We can actually just do the experiment ourselves and see which one gives us more clicks. And so we can use the images and the thumbnails to train a reward model that will allow images as input. So just ignore that I've got letters in the input. Just imagine we had a multimodal a model that can allow images. And it'll give us a positive reward for the one that got more clicks and a negative reward for the image or the thumbnail that got fewer clicks. And then we can use the reward model to train a generative AI that creates thumbnail images for us. So create an awesome thumbnail image for my new video. And we train it, and once we get Norm and Squatch on that thumbnail, we get another triple bam. That's the end. Hooray. Now, I'm no expert in business or any marketing, all that stuff, but I've been told that this is technically called dynamic creative optimization or something like that. And ad companies use it all the time. It's not just thumbnails, it's hover time on pages. They're constantly gathering this data to see how people are interacting with products and websites to optimize them, and they could do it all with reinforcement learning. So with that, I believe I've got a few minutes for questions.